I feel like Vianney's keynote is an amazing springboard for this conversation we're going to have today about building engineers. And we have it K to 12 because the whole purpose of today is for you to really understand how NGSS thoughtfully builds students' understanding of engineering K to 12. We do have this as an MSHS because we really want you to have conversations with colleagues that are similar to your own, either through teaching in an integrated model or in a domain-specific model. So don't worry, you will have opportunities to have like conversations, but we definitely want you to understand how from the kindergarten level up through grade 12, we are building the next generation of Vianney's. Today's learning outcomes, you can see them here, and we do want to make this practical, so you are going to have the opportunity to make observations, to dig deep into some standards. And in truth, we have an understanding learning outcome where we want you to know where your specific grade band fits into the bigger picture and how what you do really spirals upwards and onwards.
So we're going to start with a little bit of an intro activity, guys. So the link should be in the chat. So yeah, if you see the document that Heather just put in the chat, at the top of the document, you're going to see a link for a poll everywhere poll. And I also actually have the other link as well, if you'd like to access it that way. So I want you to think about this question. You walk into a classroom where a class is working on an engineering design project. What do you see? And please answer, don't answer with like complete sentences, just like words or phrases. What do you see? So you're using the link in the chat to answer that question. And I'll display what comes up. Can you guys see the word cloud on my screen? We are going to answer this question again at the end of the presentation to kind of see how it changes. So basically how this word cloud activity works, the bigger the word, the more people said that word, right? So collaboration is huge, especially those of you who are just in Vianney's presentation. You heard how she collaborates with thousands of engineers on her project. Engagement, which is awesome. Problem, tinkering, communication. There's a lot of words in there. Hands-on, brain, conversation, modeling, teamwork, energy, movement, messiness. I think we can all attest to that. Exploration. Give it like 5 more seconds to update. I like the art in there as well, but collaboration is a huge piece in there. Awesome. We'll come back to that question later on in the presentation
again. So if you grew up in an urban area like me, you might not have known what the phrase breaking down the silos meant. I had to go to university where there were lots of farms around, and I realized that silos were meant to hold things grown on the farm for dry storage until it got shipped out. So you do want to keep your corn separate from your wheat, separate from your soybeans. We teach children, and so we don't really need to keep our disciplines so separated. And in truth, engineering and science, there is no separation between the two. So we're really going to challenge you throughout our presentation to think beyond the discipline of science and seeing how you can maybe pull in things that are typically in a different classroom, like maybe math or social studies or health.
So in the new vision for science with NGSS, engineering is a part of that, and it's not so new anymore. But really what we're trying to do here is break down those silos. And when we do that, we're going to see less isolated engineering projects that could be less engineering at the end of the school year or standalone engineering units or engineering challenges. We know that from the pie chart, we have a lot of people that are just starting to try out engineering in their classroom. So if you're not there yet, it's okay. This is something that happens over time as you build your practice. What we will see more of is applied problem-solving skills where your engineering is embedded within your science units. And you'll also see that there's an intentional use and transfer of that knowledge to engineering. And it could even go beyond the science classroom. Engineering design is so transversal. You can see it in social studies. You might see it in language arts. You might find it in extracurricular activities, because it's really about thinking and problem solving in real world situations.
In NGSS, there's a K-12 engineering coherency. And so that means there are specific skills and concepts and knowledge that are built into the standards. And so similarly for science, if the grade band before you was like, we're not going to teach some science skills and concepts, you'd be like, oh my goodness, that's really going to mess up what I'm able to do in my grade band. It's the same for engineering. And so we have to be really thoughtful that we're addressing the knowledge, the concepts, and the skills for engineering in our grade bands so that we are able to build engineers K-12.
Today, you're going to be interacting with a lot of NGSS performance expectations, or NGSS standards. And we just want to define for you the two types of standards that you're going to be interacting with today. The first type of standard we've called crossover. We've termed a crossover standard, which means it's a standard that's a hybrid of science content and engineering. So it explains how to incorporate engineering skills into the specific science content that you're teaching as well. And I'll show you an example of that in a second. ETS standards, on the other hand, are pure engineering standards that are not tied to specific science content. As science teachers using NGSS, we're still responsible to teach the ETS standards, but it requires a little more creativity because you need to kind of dwell on them more in order to understand how you can incorporate them into your units. To give you an example of what that looks like with a middle school standard, I know we have a lot of middle school teachers in here. A middle school crossover standard is apply scientific principles to design, construct, and test a device that either minimizes or maximizes thermal energy transfer. Clearly, engineering design, one thing you'll notice in this crossover standard is that you're going to see in the DCI section, you're going to see science content, and then if I were to scroll down, you would see engineering specific content as well. So it's a crossover hybrid between the two. The ETS standards, on the other hand, there are middle school ETS standards and high school ETS standards. So they're not delineated by domain, right? So you don't have like a physical science ETS standard or a life science ETS standard. Rather, they're general ETS standards that cross over all the domains. You're going to be interacting with both of these throughout, and one thing we'll kind of have you thinking about is that if you really want your students to soar with engineering, you need to be using the ETS standards. The ETS standards really spell out the processes and skills that you want students to be following in their engineering design projects and the solutions they're trying to come up with. So using those leveraging those ETS standards in whatever unit, your engineering design unit you're using, will really level up your engineering design courses. But we'll get more into the crossover and ETS a little later on in the session.
I affectionately called the crossover standards the star standards because there's a little star at the end of like where it's written. And then Britta and John Mark told me nobody else called it that. That's just a Heather thing. So we called it the crossover because that actually makes sense to human beings. So you can thank John Mark and Britta for making things comprehensible. I am a huge NGSS framework nerd, and in the framework, it talks about the key principles and the teaching and learning shifts that are embedded in NGSS. And one of them is that science and engineering require both knowledge and practice. So they're putting engineering on an equal footing with science and saying, we need to teach knowledge and practice for science, and we also have to do it for engineering.
So speaking about that momentum that we had coming from these other conferences, we've always focused on skills, right? The science and engineering practices. We're going to be focusing a lot on the engineering practices in this conference, but we want you to know that we're not teaching you something that's brand new. It's the same 8 practices applied to problems instead of scientific phenomena. And of course, there are some scientific phenomena that are problems as well. So if you take a look at this, you can see how some of those first practices that you're doing in the inquiry cycle, asking questions, generating questions, and developing and using models, those have parallel practices in engineering design. So I'm going to give you just a moment to take a look at this rather than reading it to you. If you've come to our conferences before, we've really hit the left side, those science practices, pretty hard. And now we're going to be teaching the parallel to that, which are the engineering practices. You can see the second part of them. So again, on the right side, this is where you start with a problem and you're working through the engineering design practice to arrive at a solution. Whereas when you're doing the science practices, you start with a phenomena and you end with an explanation that you've built in order to explain how that phenomena works. In both cases, students are, as Heather says, doing the heavy lifting. They're figuring something out. They're figuring out how something works. They're solving something. So in engineering practices, they are designing solutions, arguing why those solutions are the best, and then communicating those solutions.
And on to Heather.
So when you think about what success means in science and engineering, a success in science for, the pinnacle scientists is to get that Nobel Prize, right? And that's purely for the acquisition of knowledge. And that's what our students are doing. They're gaining knowledge in science, but the application comes in engineering. So if you're an engineer like Vianney, what's going to be the pinnacle of her success? It's like when she sees Gateway, like astronauts going to Gateway and it being safe and sound, and she's able to say, wow, like what I did applied the science and it made it so that it solved a problem. Similarly, like if you're going to hire an engineer to build a bridge, you're going to really want to make sure that engineer one has the understanding of stability and instability in physical systems. And two, they also have the skills in engineering. So engineering takes that knowledge from science and puts it out in the world to solve a problem, and it stands the test of time. I'm going to tell a story about an engineering fail in my fourth grade classroom. So yes, this is back when I was baby Heather working on NGSS. And you see there's a little circle with the cardboard box. That's a seismograph. Really doesn't look like it, but it is. And so my students we were learning about earth science, which is fourth grade NGSS unit. You go to the next slide, John Mark. There was a whole bunch of, this was the context for the challenge. So we were in Malaysia, and I don't know how many people remember the Boxing Day tsunami that affected Southeast Asia and South Asia in general. We experienced massive earthquakes in Southeast Asia, and so the Ring of Fire is real. And there are also a lot of small villages in Indonesia that don't have access to electricity or to any kind of early warning system. And a lot of these villages were devastated by the Boxing Day tsunami. So I came up with this challenge. I was like, yeah, you can give them a seismograph that, is built by a big engineering firm, but they're not going to have the electricity or the expensive replacement parts. Could we build something that's lightweight, easy to replace, doesn't require electricity? My kids were on it. They were like, yes, we're building seismographs. Well, here was the little bit of the fail. What we learned in my earth science unit was all around plate tectonics and natural geological hazards. We did some weathering and erosion. What science knowledge do you need to build a seismograph? We figured out you need to know about pendulums and patterns in motion and transfer of energy. So I had a kid in my class who, I'm not kidding you, was testing at an 8th grade level for math in 4th grade on MAP. Even his seismograph wasn't working. And that's when I realized. I was like, oh, I came up with a very topical engineering challenge where, yes, seismographs do link in with earth science, but my students weren't able to apply any of their learning from the unit to this engineering challenge. So that's why when we're working on engineering, make sure we're choosing challenges that embed with the science content that our kids have.
It's like when my students used to have to make their cell cakes and Jello molds for learning the cell parts, and they really just learned how to bake, but not so much about cells. That was pre NGSS baby science teacher Britta. So anyhow, this is just to encourage you again to break down the silo. Think about how the engineering fits within the science that you're doing. That can help you avoid some of the fails. It's okay if you fail, you figure it out and you figure out how to do it better. And once you do that, once you figure out how to embed that engineering into problem solving processes within your content area, you can also look at how that might fit into or be a multidisciplinary project with language, with social studies and beyond. Welcome back, everybody. So if you kind of just felt like you were scratching the surface, that's okay. We knew that we gave you kind of a long list of standards, but those were standards to choose from. We didn't expect you to unpack them all. It was really just to kind of see how that builds and know the difference between what we call the crossover standards, where the engineering is embedded into your content standard, and then one of the pure ETS standards. So we'd love to hear from you. Did you have any aha moments today in terms of seeing that K through 12? And how did your thinking change today about K through 12 engineering? Feel free to drop answers in the chat, or if you're feeling like talking, you can raise your hand. Go ahead, Rodrigo.
Hi, everyone. Well, one of the things aha moment I saw today is that engineering is not just only designing, evaluating, refining, or creating something. It's also proposing solutions. It's also breaking down a problem into smaller or more manageable problems. When we saw those engineering standards, there were things that were not just about creating something. It was more about that engineering thinking about breaking down a problem, proposing qualitative and quantitative solutions, and things like that.
Thanks, Rodrigo. So I'm just trying to check who has their hands up. Gail, would you like to share?
Yes, I think. Okay, can you hear me? Okay, cool. Well, I think my aha was that those crossover standards, I don't think I had ever really connected the fact that they are actual engineering kind of standards, because I've been kind of getting annoyed with myself for not teaching engineering, but I actually do have a crossover standard that I teach. So it made me feel a little less bad about my not doing engineering. So.
Thanks for sharing. Yeah, it's nice that they are pre-embedded in some of the content standards, and they fit really well with what the students are being asked to perform. So it's authentic as well. Okay. Well, feel free to drop any other ahas or changes in your thinking as a result of kind of zooming out to the K through 12 and then zooming into your standards. And we will let John Mark do our last activity.
Yeah, and last but not least, we want you to go back into that poll everywhere poll and answer that same question again. So after looking through those crossover standards, those ETS standards, seeing that creative progression, you walk into a classroom where a class is working on an engineering design project. What do you see? The link is in the chat again. Answer with words or phrases. Let me go ahead and put it on the screen. A lot of testing, right? Testing solutions, prototyping solutions was a big part of those standards, defining problems, seeing criteria and constraints, right? From third grade on, students should be grappling with criteria and constraints. But definitely solving problems is what engineering is, right?
Thank you, Antonio, for your answer and reflection in the chat.
Awesome. That's awesome. Thank you for responding to that. Last but not least, if you have any questions about this presentation or anything else regarding the conference, feel free to email us at ngsspartnership@gmail.com. As far as future NGSS partnership events, we are going to have an event on May 19 after this conference, obviously, in a couple months to kind of reflect on the year. relating to NGSS. At the Tri-Association Conference in October, it's at this point, it's going to be held in person in Panama. We will be leading a pre-conference all around NGSS, so we hope to see some of you there. The virtual crash course is going to take place again in late summer for those, if you have new teachers coming to your school who are brand new to NGSS, and then we'll also plan on another conference in November. I feel like we're kind of getting ahead of ourselves a little bit because we're just starting this conference, but thanks so much for coming to this session, and we look forward to seeing you at the rest of the sessions throughout the conference.
Thanks, everybody. Happy
Have a great time.
NGSSing.
Thank
Have a
you.
great time with Paul at his engineering session coming up next. And we will see you throughout the days.
The Paul's session starts in 4 minutes.